Okay, so let's continue what we were discussing yesterday. So what I mentioned at the end of yesterday's lecture was that if you look at a non-integrable quantum system, and if you could somehow calculate its energy eigenvalues, and you looked in the middle of the spectrum where the density of states was sufficiently large, you had a large number of energy eigenstates within some interval. And if you looked at the statistics of those energy eigenstates, specifically the level spacing statistics, which means that you look at this interval, you look at the energy eigenstates in the interval, and then you arrange them in, say, ascending order of the energies and look at successive differences of energy and look at the statistics of that difference, then that has a form which is quite distinct from what you have for an integrable system. An integrable system, that is Poissonian, it's a Poisson distribution. And for these systems which are not integrable, that form is quite a bit different. And the most striking difference compared to the Poisson distribution is that if you look at this distribution function, so S here is the difference in energy between successive levels in units of the mean level spacing. So this was defined in the last lecture, so I can write it down again. So S is equal to delta E divided by delta E mean. Okay, so it's the energy difference in units of the mean level spacing. So this goes to 0 as S goes to 0, so which tells you that the probability of finding two energy levels whose energy difference is much smaller than the mean level spacing is very small. In fact, it goes to 0 as that energy difference goes to 0, which of course is a striking difference as compared to the Poisson distribution, where P of S is a monotonically decreasing function of S. So it actually has its largest value as S goes to 0. And then I also wrote down two forms for P of S. So I said that so the way in which one can make this argument is by arguing that if you were to look at the Hamiltonian, if you now take the Hamiltonian of the system and project the Hamiltonian onto this, this space in this region in the energy eigenspace where you're looking, and if you then, if you look at the Hamiltonian matrix that you get, that Hamiltonian matrix, when expressed in some generic basis, is going to look random. Okay? So today we'll discuss that a little bit more, where that idea is coming from. So then you say that for non-integrable systems, the Hamiltonians that describe the non-integrable systems in generic bases look random, okay, at least in some energy window. And something like this would follow from just looking at the statistics of eigenstates or eigenvalues of random matrices. Right? And so with that argument, or with that line of argument, one can actually do better than this. We can actually calculate these functional forms. And this is what I'd written down right at the end of yesterday's lecture. That for a certain class of Hamiltonians which have a certain property, namely time reversal invariance, this turns out to look like this, okay? And the corresponding random matrix class, the corresponding ensemble of random matrices, right, which would give you this, which this particular Hamiltonian would be a member of, is called the Gaussian orthogonal ensemble. Okay, so that's one such class. And what's special about this ensemble is that the random matrices in this ensemble in generic bases can be expressed as real symmetric matrices. Okay? So a Hamiltonian in general is a complex Hermitian matrix, but for systems which have this property, which belong to the Gaussian orthogonal ensemble, in a generic basis, they can be expressed in such a way that they're real symmetric matrices. So you only have to worry about the statistics um, of a collection of real symmetric matrices with random entries, and that gives you this. So we will actually look at how that derivation proceeds in just a little bit. So that's one class. Then there's another class. Yeah. Right. So there are going to be deviations at large S. In fact, the derivation of this that I'm going to present is really going to be for an ensemble of 2 by 2 matrices. And if you wanted to generalize this to n by n matrices, which is what we want, then it's not exactly going to be this. There are going to be deviations from this. And especially, I guess well, okay, so what we know is that as S goes to infinity, this does have to go to 0. I guess your question is, does it go to 0 in this particular way? So for an ensemble of 2 by 2 matrices, it does, because you can derive this exactly. But for n by n matrices, there are going to be deviations. Well, no, okay, so here's the thing. See, that we have accounted for. So you're talking about energy differences, okay? Which is the reason that we divide by the mean level spacing. Now, what's going to happen is as you increase the size of your system, the number of degrees of freedom, your energy levels in terms of the energy difference between them are going to come closer, okay? And so so in this language, what that means is that the mean level spacing is going to go down. And in fact, the mean level spacing is going to go down exponentially with the size of the system, okay? But that is not what we are saying here. What we are saying here is that you take that into account by dividing all the energy differences by this mean level spacing, meaning that all the energy differences are going down exponentially with the size of the system, okay? Not just the mean level spacing, the smallest one that you have. For instance, let's say you look at the smallest energy difference for a certain system of a certain size, and you look at the smallest energy difference for a system of a larger size, you will see that the energy difference for the larger size system is going to be smaller than for the smaller size system, and it will keep going down exponentially with system size, okay? That will happen for all the delta E's. So the way to remove that is by dividing by the mean level spacing. So all those exponentials cancel. And this then is, at least for sufficiently large systems, is now something where there's no dependence on the system sizing. Okay? All right. And then there's this. Which corresponds to, so this is abbreviated to GOE, and this is the Gaussian unitary ensemble, which is an ensemble of complex Hermitian matrices. Okay. Now, I should mention that there's a third ensemble, which is something called the Gaussian symplectic ensemble. Okay, so before I go there, so this corresponds to having time reversal invariance. This corresponds to having no time reversal invariance. Okay, so you can think of physical Hamiltonians that belong to this ensemble as those where there's a magnetic field or something which breaks time reversal invariance. And there's also a third ensemble, which is important, which is something called the Gaussian symplectic ensemble, which I will not discuss in detail. So you can think of the Gaussian symplectic ensemble as being an ensemble of matrices where the entries are not complex numbers or real numbers, but are objects called quaternions. So I don't know if you're familiar with quaternions, the similarities between quaternions and 2 by 2 matrices. So you can sort of think of those Hamiltonians as Hamiltonians whose elements are not simple numbers, real or complex, but actually these quaternions. And so there are physical contexts in which those arise as well in systems with spin-orbit coupling. And for those, it turns out that there's a different form, and that's called the Gaussian symplectic ensemble. And the main difference is that Here you can see as s goes to 0, p of s goes to 0 linearly. Here it goes to 0 quadratically. For that ensemble, s goes to 0 as the fourth power. Okay, but anyway, so that's not something which I'm going to talk about anymore. So now you can ask, well, where do these come from? Okay, so we're going to look at that in just a little bit. But the history of the subject was actually quite interesting. So this goes back to Eugene Wigner, who realized that for a sufficiently complicated quantum system, something which had lots of degrees of freedom which were interacting with one another, it was absolutely hopeless to try to calculate the energy eigenvalues exactly. I mean, you could do it for reasonably simple systems, the ones that you encounter in typical beginning quantum mechanics courses. But if you have something like, even if you have an atom which is not a hydrogen atom with with many electrons, and you took into account the interaction between the electrons, or in this particular in the context in which Wigner was thinking, if you looked at the nucleus and which had a fairly large number of nucleons, and you looked at the interactions between the nucleons and tried to calculate the eigen energies of the nucleus, that was a hopeless task because the Hamiltonian was extremely complicated. But his insight was that just because it was a hopeless task didn't mean that you couldn't make any progress with predicting physical properties or even saying things about the spectra of these things. And so what he realized was the thing that made it hopeless to try to solve the problem exactly was actually what simplified things when you looked at it this way. The fact that the Hamiltonian in some sense didn't have any structure, the Hamiltonian didn't have any symmetries that you could exploit to try to diagonalize it. In fact, in some generic random basis, the Hamiltonian looked completely random. Okay? And that's the thing which got in the way of trying to diagonalize it and get its energy eigenvalues. But his insight was to see that the same thing which is proving to be an impediment in terms of getting energy eigenvalues could actually help you in terms of looking at differences of energy eigenvalues. Okay? That actually turned out to be something with some structure. And in fact, that structure is this. So one of the first successes of random matrix theory, and I'll show you the data in just a little bit, was to be able to explain the differences in energies of nuclei that were observed from various experiments. So experiments were able to look at differences in energy, successive energy levels of heavy nuclei. And it appeared that that looked fairly regular in some sense. And Wigner was able to explain that on the basis of random matrix theory. And then Freeman Dyson took that idea forward and looked. I think he's the one who actually looked at these different ensembles. So these kinds of distributions which arise in random matrix theory are also called Wigner-Dyson distributions. So quite often the term Wigner-Dyson distribution is going to be used generically for these kinds of random matrix distributions. That's used quite often. When you don't, for some reason, have to specify whether it's GOE or GUE or GSE or something, just use this generic term. Okay, yeah. Okay, so right now I'm really not even talking about thermalization yet. Okay, I'll come to thermalization in just a bit. So the way we arrived here, because let me just jog your memory about what we did to get to this point. So what we said was that, we said, okay, let's try to look for chaos in a quantum system and let's see how we can define chaos. And then we argued that the standard way of looking at diverging trajectories and saying that the trajectories, the distance between trajectories was diverging exponentially with time doesn't work for a quantum system because of its simple dynamics. Okay? And then we said that we would look at chaos in quantum systems by first characterizing what chaos is not in classical systems and looking at the equivalent of that, which was integrable systems. And then we said, okay, fine, now that we know what chaos is not in a quantum system, let's look at the opposite of that and say that that is chaos. And that was what was brought us here, okay? So we are still thinking of an entire quantum system without worrying about subsystems yet, okay? So then you might now say, well, if I'm looking at a quantum system, in order for me to do statistics, Do I need to have a sufficiently large number of energy eigenstates in order to even look at a statistical description? The answer is yes, okay? But fortunately, that's not such a big deal, because what we need is a large number of eigenstates. We need a sufficiently large Hilbert space. And the Hilbert space is something whose size is growing exponentially with the number of degrees of freedom. Okay? So what that tells you is that even if you have a fairly modest number of degrees of freedom, and I'll show you numerical data on such systems. Okay? So if you have a lattice system with, say, 12 lattice sites, and 12 is certainly not 10 to the power of 23 or something, or not even 100 or something like that. That is still okay for doing calculations like this, because the Hilbert space dimension for that is going to be exponential of 12. Okay, that's one way of defining it, yes. No, it's not the difference of two. It's the distance between, it's not really, okay. You start the system out in some initial state, okay, which is a particular microstate. Look at its evolution. As it evolves, it goes to other microstates. Start the system out in another microstate, which is very close to the earlier one. Look at the evolution of this microstate, and look at how, right. No, so that's exactly what we discussed yesterday, right? That we said that in a quantum system, if you wanted to import the same idea into quantum mechanics, then you'd first have to define a distance between trajectories, okay? You'd have to define a distance between microstates as they were evolving. And then we said that the natural notion of distance was in terms of the inner product, but the unitary evolution preserves the inner product, so that distance is not going to change. Whatever distance you started with, by that definition of distance, is going to continue to be the distance. Well, okay, so you have to be clear about what you mean by chaos for a quantum system, okay? And so my point was that in order, one notion of chaos is to look at some other notion of chaos for a classical system, which can be taken and also applied to a quantum system. And what was that? So that notion was the notion of not having chaos in a classical system, having an integrable system, which has an analog. And then you say that systems which are not integrable are chaotic. So that was sort of the way people, I'm not saying that this is the only way people talk about quantum chaos. Indeed, characterizing chaos in a quantum system, what that actually means, is a large industry in itself. A lot of people have worked on it. But this is something which is a fairly generally accepted point of view. And that's the reason I'm presenting it. And for that matter, what chaos means for a classical system also doesn't have any unique definition. But anyway, let's not get into that, because that's a fairly complicated thing. Okay. All right. So now you can ask, well, where do these things come from? So it turns out that you can actually get distributions like this by looking at the smallest size quantum system that you can think of, which is a system with a Hilbert space dimension of 2, which means that any operator or a Hamiltonian in that quantum system is going to be a 2 by 2 matrix. So what you can do is you can take 2 by 2 matrices, okay, which belong to these ensembles. So you can look at an ensemble of 2 by 2 real symmetric matrices, okay, and then with random entries, and then try to calculate quantities of this sort. Okay. So it turns out that you can do that, and in fact you get, so these formulas that I've written down are actually for such 2 by 2 systems. So let me just tell you how that calculation proceeds. So what you do is you do the following. So you look at a 2 by 2 Hamiltonian. Okay. And I'm going to confine myself only to these two, so no quaternions. So we're just talking about a Hamiltonian whose entries are numbers. So the most general kind of 2 by 2 Hamiltonian, or the most general kind of 2 by 2 Hermitian matrix, is something which is going to have this form: epsilon 1, epsilon 2. And if you just write it like this, and in a little bit you'll see why I have written it like this. Okay? So what we know is that, so this is in general a Hermitian matrix. So the diagonal entries have to be real, and the off-diagonal entries have to be complex conjugates of each other. So this is the most general 2 by 2 Hermitian matrix. Now, if we were dealing with real symmetric matrices, then V would also be real. Epsilon 1 and epsilon 2 have to be real. V would also be real. And then that would be a family of real symmetric matrices. But this is the general family of complex summation matrices. Okay? So now if you want to describe a family of random matrices of this sort, so then what we do is we say that these are random variables. Okay? And these are random variables which have all been plucked from the same distribution. So all of these, epsilon 1, epsilon. All right. So now you can, so what we're interested in is the level spacing distribution. So in this particular case, there are only two levels. Okay, so there's only one spacing. There's only one difference of energies. And so that difference of energies here for a Hamiltonian which looks like this is just simply, oh, what happened? I should be able to do this without looking at my notes. So delta E is going to be equal to I guess that's what it is. And yes, that's what it is. So what we want is the statistics of this, given that this is, that each of the individual components have statistics like this. So what I'm going to do now is, I'm not going to do that derivation. I'm going to leave it as an exercise for you and just tell you that if you were to do that, then you would get, if you were to do that calculation, you would actually see it's equal to this. But remember that in order to write the level spacing distribution in this form, you have to divide delta E by the mean level spacing. So what we want is, we want the probability distribution for delta E in units of the mean level spacing, meaning in units of the mean of this quantity. Okay, that's what S is. And that will turn out to be equal to that, all right, for the GOE distribution. Now, if you look at the GUE, the Gaussian unitary ensemble, it's exactly the same calculation. The only difference is that V now is complex. Okay, it's not real. So it has two real components. So there's a V real and a V imaginary. And you have to assume that V real and V imaginary are independent of each other and drawn from the same distribution. So at this point, you're going to have a V real squared plus a V imaginary squared. But this is still going to be the same. This is not going to change. But because you have an extra random variable now, instead of 3 random variables, you've got 4 random variables, it turns out that, these things are going to change. And so finally, you will end up with a different distribution, okay? So the fact that you have a different power here is just related to having an extra random variable. But with that extra random variable, you're going to get this. So this is the way in which you can get those distributions. But now the point is that, we've got these for 2 by 2 matrices. But the claim that we're making is that if you look at an n by n matrix, right, then that looks like it's been plucked from some random distribution, or say some random family of n by n matrices. And you might expect that if you were to do that calculation for n by n matrices instead of 2 by 2 matrices, you would get something which is very different from this. But it turns out that that isn't the case, okay? The reason that we do it for 2 by 2 matrices is that it's simplest to do it for 2 by 2 matrices, okay? Doing it for a general n by n matrix is really impossible. But then there are arguments which tell you, and I'm not going to go into them, because they are involved, and I'm by no means an expert on all of those arguments, that if you were to look at the spectrum of such matrices, then there is a way in which you can think of them as that spectrum coming from some kind of a direct product of random 2 by 2 matrices like this, and then you can do the calculation on these 2 by 2 matrices, and the same result essentially applies to the n by n matrices, but it doesn't exactly apply. There are differences, as John Cardy was mentioned, and especially down in the tails. But this signature of how P of S goes to 0 as S goes to 0 is reasonably robust. And the reason we know this is that we can actually do these calculations numerically on large dimensional matrices and check all of this. Okay. So that's so the signature, so the difference between what you see, what you expect for an integrable system and a non-integrable system lies in the level spacing. There are other differences as well, but this is the most striking one and is typically the one that is used to distinguish between these two families of systems. Okay. All right. So still no mention of thermalization in this context, no mention of expectation values of observables and things like that. So we'll come to that next. All right. So I'm going to write down these two lines here, just to sort of quickly summarize what we've done so far. So integrable and Poissonian statistics and non-chaotic can be used interchangeably in a quantum context, and the opposites of these, non-integrable and Wigner-Dyson and chaotic are also used interchangeably. Okay, so if you read the literature on this subject, especially the recent literature on things like many-body localization, then these terms are used to mean one another, this set of terms, and similarly this set of terms are used to mean one another. Okay. All right. So note, of course, that all this, there's no rigorous proof. I mean, in some sense, we are defining, if you like, non-integrability in these terms. So it turns out that it's not really as ad hoc and random as I've made it out to be. There is a conjecture based on a calculation by Boigas, Giannoni, and Schmidt, which goes back to the 80s, which states that if you take a classically chaotic system, something which you have characterized as chaotic in a classical context, where the characterization of chaos is better, chaos is a more well-defined concept, right? And then if you looked at its quantum counterpart, meaning that you had some way in which you could convert the variables of that into operators, canonically conjugate variables into operators, replace Poisson brackets by commutators, then the conjecture is that this has Wigner-Dyson statistics and this was proven by these people for a particular kind of classically chaotic billiard system, where they actually were able to do this, show explicitly that the spectrum has Wigner-Dyson statistics. And because that worked out so well, it was raised to the level of a general conjecture, but it is a conjecture. It's called the VGS conjecture. But this is at least one system where you know that classical chaos, when quantized, is giving you Wigner-Dyson statistics. All right. So no, okay. So what we are saying is that we're just saying look at 2 by 2 matrices which are random. In what sense are they random? So first of all, ask what kind of 2 by 2 matrix can be a Hamiltonian. What was the general form of a 2 by 2 Hamiltonian? The general form is this, okay? Now we want random Hamiltonians. So we want these entries to be random. What does it mean for the entries to be random, okay? So I'm saying that what it means for the entries to be random is that A, these are uncorrelated, Okay, which means that if you look at a whole collection of these Hamiltonians, and you look at, in that collection of Hamiltonians, if you were to look at the correlation between this entry and that entry, you would find that they are uncorrelated. Okay, that's the first thing. The second thing is that all of these are drawn from the same distribution. So these are random variables. They have to be drawn from some distribution, and they're drawn from a Gaussian distribution with this width. Okay. So the fact that this corresponds to a chaotic system is something which I'm not particularly concerned about here. I'm just looking at the properties of random Hamiltonians, and saying that if you were to now look at the distribution of level spacings for this, then the distribution of level spacings would look like that. Yeah. Yeah. Oh no, not as far as I know, not really in closed form, because that's very difficult to do for a general N. So what people see, so there are, as I said, conjectures that it's going to be the same for, and arguments that it's going to be the same for what you get for a 2 by 2 matrix. But then if you want to check that, right? I mean, those are not mathematical proofs as far as I know. So if you want to check that, then the only thing that you can do is take an N by N system and then obtain the energy eigenvalues in some way, typically by numerical exact diagonalization, and see if they fit this. And they do to a remarkable degree, and I'll show you later. Yeah, but you have to realize that the real success of this came from the fact that you could do this calculation, get this, and it fit what looked like highly complicated data on nuclear spectrum, right? On some very complicated system, the energy level spacing statistics fit this. So okay, so I think the point here is that if you were to draw these from a different distribution, then of course it would look different for something as small as a 2 by 2 matrix. Okay, but then if you're actually interested in looking at N by N matrices, which are particularly large, right? And if you wanted to look at, but you have a large number of these, large number of entries, and you're looking at a level spacing distribution of something like this, which is going to involve many of these things summed in some way, then the central limit theorem is going to tell you that that final thing is, you could probably get the distributions of individual eigenvalues for that, of individual eigenvalues from some sort of Gaussian distribution. And then you can go back and say, look, if that's a Gaussian distribution, then I could have got to that Gaussian distribution starting from something simpler to begin, something which I have a better handle on for the smaller system, and I start with the Gaussian. See, for those of you who are familiar with the spin glass literature, for instance, right? So this kind of thing comes up in the spin glass literature all the time, that you have some random distribution of spin-spin couplings, and you have to take that, and you have to take those couplings from some distribution. And what you do is you take those couplings from a Gaussian distribution, because of the fact that you can do the calculation easily for a Gaussian distribution. You can average over a Gaussian, you can do Gaussian integrals. So if you're familiar with something like the Sherrington-Kirkpatrick model, that's what's done there. And then you sort of say that, look, the fact that I started with a Gaussian distribution doesn't matter because of the large degrees of freedom that are involved. I hope that's sort of wrong statement. So it's sort of in the same spirit. Any other questions? Okay, fine. All right, so okay, so one thing which I should mention at this point is that another reason that integrable systems are special is that if you wanted to make a connection between classical and quantum systems, then the eigenstates of integrable systems actually correspond to these periodic classical orbits. And then, through this Wilson-Sommerfeld quantization that I talked about in the last lecture. But if you wanted to think of the eigenstates of non-integrables, the eigenstates of non-integrable systems in terms of some orbits of the corresponding classical chaotic system, then it's not very clear how to make that, it's not very clear how you can quantize chaotic orbits in order to get the energy levels of a non-integrable system and the energy eigen, and to get the energy eigenvalues of a non-integrable system, starting from chaotic orbits of the corresponding classical system is something that is not clear, but it is, reasonably well-established procedure here. So there's really no meaningful sense in which you can talk about the eigenstates of a non-integrable system, think of them in terms of classical trajectories. Because then if you could do that, then there would be some way to quantize the classical trajectories to give you the corresponding eigenvalues. And that's not a very, people have worked on this, but it's something where the connection is rather tenuous. Okay, fine. So, all right. So now let's look at matrix elements of operators, because that is the kind of thing that we're interested in when we are talking about thermalization, all right? So for the time being, let's just forget about the following fact, okay? Let's just forget about the fact that we were looking at some actual system and looking at the middle of, looking at some part of the energy spectrum of that where the density of states was large and sort of focusing on that part of the spectrum. Let us just do something a little more generally, and we'll come back to looking at a particular part of the spectrum of the system in some time. So let's just assume that you have some Hilbert space. Okay, on which you have these random Hamiltonians that are defined. So some Hilbert space on which you have these random either complex Hermitian matrices or real symmetric matrices, which you're going to call Hamiltonians. And they have, this energy level spacing distribution. And now you want to look at the eigenstates. So far we've been looking at the eigenvalues. You want to look at the eigenstates of these Hamiltonians and then calculate matrix elements of operators in those eigenstates. And why do you want to do that? Because if you can calculate the matrix elements of operators in eigenstates of any Hamiltonian, then you can calculate the matrix elements of operators between in any state of that Hilbert space, right? Because you can write down any state of that Hilbert space as a linear combination of energy eigenstates, okay? So what we're going to do is, so there's a Hilbert space on which there are random Hamiltonians. Okay. And what we're interested in is calculating the matrix element of some operator defined on the same Hilbert space, which looks like this. Okay, so let's say M and N are eigenstates of a Hamiltonian on this Hilbert space. Okay, so what we're interested in is calculating objects like this. And when I say calculating objects like this, what I mean is again looking at some kind of distribution of objects like this. Okay, so if I took this operator, expressed it as a matrix in the eigenbasis of some Hamiltonian, okay, and I looked at different random Hamiltonians and expressed the this operator in the eigenbases of those random Hamiltonians, then I'm going to get a bunch of different matrices corresponding to this operator. And I can then ask about the statistics of those matrices, ask about what the entry, the components of those matrices look like and what their statistics are, given what we know about what happens for random Hamiltonians, what we've seen so far, okay? But it turns out that we need, something which in some sense logically follows from everything that we've done, but something that needs to be specified before we attempt to do this, okay? So we've not said anything about the eigenstates yet. We've only talked about the eigenvectors, sorry, the eigenvalues and the level spacing distribution. So you can ask, well, what does this tell us about the eigenstates of random Hamiltonians? So you would expect the eigenstates of random Hamiltonians, so the eigenstates of column vectors, to also look random. Okay, so if you take some Hamiltonian which is random in some basis, some family of Hamiltonians which look random in some basis, and you look at their eigenvectors, okay, then you wouldn't expect those eigenvectors to have any structure because they were eigenvectors of random Hamiltonians. So this is sort of, again, this is a notion, it's not a proof, but this is another one of Berry's conjectures. That the eigenvectors of random, actually not random, his conjecture is that the eigenvectors of non-integrable Hamiltonians look random in, again, generic bases. All right. So here, so the conjecture, it really boils down to saying that non-integrable Hamiltonians are like random Hamiltonians, because saying that the eigenvectors of random Hamiltonians look random in some generic basis is not so much of a conjecture, but saying that non-integrable Hamiltonians are random is really where the main part of the conjecture is. Okay. So of course, note that I've said in generic bases. Now, what are the generic bases? Okay, so the generic basis is something which is not special to a particular Hamiltonian. Now, every Hamiltonian has one basis which is very special to it, right? Which is the basis of its eigenfunctions. So if you were to look at the eigenvectors of that Hamiltonian in that basis, they will not look random at all. They have, they're perfectly structured. You have one entry which is 1, everything else which is 0, right? That doesn't look random. That is not what this is about. This is about saying that I give you a Hilbert space, and then you sort of close your eyes and somehow, you dip into that Hilbert space, pull out a basis, an orthonormal basis, and then I express my Hamiltonian in that basis for you. The odds that you will pull out the basis in which that Hamiltonian is diagonal is going to essentially be 0 for a large enough Hilbert space. So anything which you pull out will be a generic basis, and in that generic basis, any non-integrable Hamiltonian is going to look random, and hence its eigenvectors are going to look random. Okay, that is what this is saying. Okay, so given that fact, what can we say about something like this? All right. So the way that that proceeds is by saying, so this is some operator. Now this operator has its own basis in which it is diagonal, which is this one. That's the reason I've been able to write it like this. Okay. So the basis of vectors I is the basis in which this operator is diagonal. Now such a basis for some general operator is as good as, is essentially a random basis for the Hamiltonian. There's no reason for some general operator, there's no reason for its eigenbasis to have any correlation with the eigenbasis of some Hamiltonian that you've given. Okay? So for the purpose of this calculation, this basis is generic enough. Okay. So what we need to do is we need to calculate this kind of object given that m and n are random vectors in this basis. Okay. All right. So then we can write n as summation over I, C n I, and we can write m similarly as a summation over I, C m I. So we can express these as a linear combination of those. Okay. Okay, let me just change the notation to be consistent with my notes. My notes, I have these written as psi and not as c, because I think I've used c for something else later on. Let's call these psi's. So these psi's are some complex numbers. Okay, so then m o n, this thing which was o m n, is going to look like this. Sorry, excuse me. Okay. So that's what this is going to look like. And what we need is, we need statistics of this. So we can first ask, so there's going to be some distribution for this because these are random. So we can first ask what is the mean of that distribution. Okay, so what is the mean value of this? Okay. So the mean value of this is going to be summation over I, OI, the mean value of that. Okay? And remember that these are random numbers. And you can convince yourselves, and if you're finding it difficult to convince yourselves of this, we can go over this quickly, that this is going to be equal to that, where D is the dimension of the Hilbert space. Okay. So does everyone see this, or do you not see this? I'm assuming, of course, that these are normalized. I mean, I've assumed that these are normalized, which is the reason you get the 1 over D in the denominator. But does everyone see this, or does everyone not? Does someone not see it? What is it averaged over? It is averaged over random vectors like this. It's averaged over these. So you take random Hamiltonians, look at their eigenvectors, okay, some ensemble of random Hamiltonians, look at their eigenvectors, pick 2 eigenvectors for each member of that ensemble, okay, and then average over the all. Our states M and N are random, meaning that these numbers which appear here are random, okay. So this is a statement about those numbers. Right, right. These are not random, these are some, right. Yes. Okay, fine. No, there's no, I'm not talking about any subsystems yet. No, look, here there's no, I'm just looking at the entire Hilbert space. I'm not trying to partition the Hilbert space into a subsystem and a bus, okay? So there is no notion of any subsystem here. I'm saying that there's a Hilbert space on which you have Hamiltonians, you have other operators. Pick a particular operator which looks like this, okay, and ask about its matrix elements in between eigenvectors of random Hamiltonians, okay. All right, so when you have this, now you can easily, so now you can see that with this, the average value of OMM, okay, is going to be equal to, excuse me, actually, okay, let me just write this down one time. So the average value of OMN given this is just going to be equal to 1 over D summation I OI delta Mn, okay, which means that if you're looking at the average values, the off-diagonal elements are on an average going to be equal to 0, and the diagonal elements are going to be equal to 1 over D summation I OI. And what is 1 over D summation I OI? 1 over D summation I OI is basically the average of this. So it's the average of the eigenvalues of the operator O is what this is. So this is going to be equal to O average delta Mn. Note that I've removed any discussion of focusing on an energy window from this, and you'll see why that's important in just a little bit. So right now I'm saying, just think of some Hilbert space on which you can define these operators and these Hamiltonians. And then if you were to look at the statistics of these matrix elements, you will find that the averages look like this, okay? But we can now, but remember that, we're looking at statistics, so averages are not enough. We can look at, we have to look at fluctuations about those averages. So we need to look at quantities like this, which are fluctuations about those averages, okay? And what is the definition of something like this? So this is going to be okay. So what does this mean? So this means that you look at these random Hamiltonians, right? This ensemble of random Hamiltonians, pick out an mth eigenstate and an nth eigenstate for each member, okay? And between the mth and the nth eigenstate, calculate these quantities. And so you get a list, one for each member of the ensemble. And then the average of that is going to be this. You will get a zero average unless m and n are the same. And now you can ask, well, what is the standard deviation? Or what is the variance um, of that? And that is going to be characterized by this kind of quantity, which is a fluctuation. So we can calculate this as well, because we know what these quantities are, okay? We know what OMN is. OMN is just given by this thing here, so we can just plug this in there. So what you'll find is that for m equal to n, this is going to be, and you can do the calculation, for m equal to n, delta OMM squared. So this is the fluctuation in the diagonal entries is going to be equal to summation OI squared times this minus that. Okay? So summation IOI squared times the average of the fourth moment of this distribution minus minus the square of the average of the second moment of the distribution. Okay? And this is going to be equal to for GOE distribution, and this is going to be equal to once again, I'd urge you to try to show this. Now, one of the things which is important here and which you might have encountered in other contexts is that for Gaussian distributions, there is a relation between the fourth moment of the distribution and the square of the second moment. So if you have a Gaussian distribution for a real variable, does anyone know what that relation is? So have you ever seen things like this? So if x is a Gaussian distributed real random variable with mean 0, let's say, does anyone know what this is equal to? Okay. So exercise. Show that it's equal to 3. And so this is actually something which is used to characterize Gaussians. So if I give you something which looks like this, okay, I just give you some data, and I assert to you that it's a Gaussian, just because it has this qualitative form, how do you know that it's a Gaussian? So one way of measuring its Gaussianness is by calculating this and seeing how close it is to 3, okay? So that goes into this, into getting these numbers here, but you have to be careful because, and the reason you get different numbers is that in one case this is a real variable, in the other case it's a complex variable. All right. So this is what we get, and so what we have is basically, so one way of summarizing the fact that the mean looks like this and the variance looks like that is to say that if you were to look at OMN, the M, this particular entry for O in one of these members, for some particular value of M and N of some particular Hamiltonian from the ensemble, then it's essentially going to look like this. I'm going to write this essential equality form. I mean, it's as good as saying what's on the right-hand side, but not exactly that. So this is going to be where Rmn is some random variable of 0 mean and unit variance, okay? So what this is saying is that if you now look at this matrix element in some random, in the eigenbasis of some random Hamiltonian, then it's going to essentially look like this, meaning the diagonal entries are going to have this value, the off diagonal entries are essentially going to be 0, but with fluctuations of this order. That's what this means. That's what this funny equality sign means, okay? It is not asserting that if you were to just randomly pull out some Hamiltonian from the ensemble and calculate OMN in its eigenbasis, it's exactly going to be equal to this, because that's absurd. It can't be the same for everything. But this is what the structure is going to be. You will find, right, if you look at different such Hamiltonians and look at OMN, what you'll find is that on an average, OMN is going to do this with fluctuations which are of this order, okay? And D here is the Hilbert space dimension. So this is one way in which you can see macroscopic thermalization in random matrix theory. Okay, so now we are going to talk about thermalization. So what do I mean by macroscopic thermalization here? So I'm not, okay, so if you say that the Hilbert space that we were looking at was actually now some slice of the energy spectrum of some Hamiltonian, and if you said that this operator that we have here, that these are the eigen, when you write down its diagonal representation like this, that these i's are, if you calculate the expectation value of energy of these i's, okay, then those lie in that slice with a very small spread, then you can just think of the calculation that we did as corresponding to a particular slice of the spectrum. And in that slice, what we found is that if you look at a particular operator and you look at its matrix elements in this eigenbasis, then the matrix elements are like this, where this is the microcanonical value. This is the value of the operator when averaged over that particular slice of energy. Okay? And of course, you have fluctuations like this on top of it. But the point is that those fluctuations are going down as 1 over square root of D, where D is the Hilbert space dimension. And this is in some sense how small this is actually worse than it looks, because D is the Hilbert space dimension. And if you ask what this means in terms of the number of degrees of freedom of the system, that is going to be, so D is exponentially large in the number of degrees of freedom, right? So which means that if you have n particles or n spins or whatever, then D is going to go as exponential of n. So this fluctuation about this value is going down exponentially in the number of degrees of freedom that you have. Okay? So it is essentially what you have for, so in each energy eigenstate, the value of this, the expectation value of this typical operator is essentially equal to the microcanonical average. Microcanonical here being defined as average over this entire Hilbert space that we've looked at, okay? Now you can convince yourselves from this, so this is only looking at the expectation values for these eigenstates. Now what you can do is you can take any random state, which is some linear superposition of such eigenstates, and calculate what the expectation value of O is in such a state, with given what we know about these eigenstates, and again convince yourselves that for any such state, you will find that the expectation value is O bar with fluctuations which are falling off exponentially in the number of degrees of freedom. Okay? So this is how random matrix theory in this sense gives you thermalization in the sense of mate that I had defined earlier. So this is some typical operator. But here we've glossed over certain important things. For instance, we haven't really been very careful about connecting something like this for some Hilbert space, for some general Hilbert space, and saying that all of this works when that Hilbert space is in some is basically some energy slice of the total spectrum. So what that means is that if you wanted to extend these kinds of ideas to something that's more realistic, you will have to put in energy dependencies. See, right now, this object here is just some object for the whole Hilbert space, okay? But if we assert that the Hilbert space we are talking about here is actually some slice from the spectrum of the full Hamiltonian, then in general, you would expect this to have some dependence on which slice we are looking at, right? And each slice is centered around some energy. So in general, you would expect this to have some energy dependence, okay? And also, excuse me, here for instance, this thing that we have here has no dependence on the m's and the n's, meaning it's the same thing regardless of which m and which n we pick, meaning that in this Hilbert space, it doesn't matter which eigenstate m and which eigenstate n we pick. Now that is fine in, for this for these random Hamiltonians in this Hilbert space which we considered, because there's no way to distinguish one m from another n. But the moment you talk about energies, right, and being in a particular energy window, then you have to worry about whether, how close the m's and the n's you're looking at are to the extremes of this energy window, right? So you have some energy window now, which is this Hilbert space, and there's some m and some n in here, and you might expect that what you have for the off-diagonal elements will depend on how close these m's and n's are to these extremes, right? So, so those are refinements which are not there in random matrix theory, and these are the refinements which were put into, in some sense, random matrix theory about 2.5 decades ago, and they go by the name of the eigenstate thermalization hypothesis. Okay? But even before we go into the eigenstate thermalization hypothesis, you can already see a germ of that idea here. So what that's telling you is that if you look at a particular eigenstate, m equal to n, right, the expectation value of O in that eigenstate is equal to its average value, is equal to its microcanonical average. The only thing is we've thrown out details like energy dependence and the dependence of these, and the dependence of the off-diagonal elements on energy and energy differences and so on, okay? But the basic idea that eigenstates look thermal is contained here. So the refinement of this idea is the eigenstate thermalization hypothesis, which puts in everything that we've glossed over here, which we've thrown out. It is a hypothesis. There is no proof of this, okay? But what the hypothesis does is it hypothesizes about what the actual structure of something like that is, okay? So let me just write down the statement of the eigenstate thermalization hypothesis as soon as I can get my notes in order. I should have really stapled them together, but okay, yeah, all right. So the eigenstate thermalization hypothesis states this. Abbreviated to ETH for short, and this goes back to Joshua Deutsch and Mark Srednicki from the early 90s. So Deutsch was the person who first sort of, refined some of these random matrix theory ideas to explicitly talk about macroscopic thermalization. And then Srednicki is the person who came up with the form of OMN that I'm going to write down. So the eigenstate thermalization hypothesis states that OMN times Rmn, where what we're doing now is we're actually looking at a many-body, we're looking at some system, we're looking at its energy spectrum, and focusing on some interval in that spectrum, okay, with a certain width. And so within that interval, there is an average energy. So the eigenstate thermalization hypothesis says that if you look at the expectation values of typical macroscopic operators between the matrix elements of this for energy eigenstates in that window, then those have a form which looks like this, okay? So the diagonal elements are essentially the same, and they have this form, the value of this macroscopic operator at the average energy. So meaning that if you were to sort of, this is really the microcanonical average. So if you were to look at the expectation value of this operator at all the energy eigenstates in this window, in this interval, and then averaged over that value, then that is what this is, okay? So that's what the diagonal elements look like on an average. And then you have these fluctuations. So the off-diagonal elements on an average are 0. The diagonal elements have this form. And then you have this for the fluctuations, okay? So Rmn is still the same Rmn as before. It's a random variable with 0 mean and variance equal to 1. But now you can see that there's more structure here. So, okay, so I should actually be clear about this. So E bar is really this, and omega is equal to Em minus En. So when I said average, I really meant it in this sense. But of course, for systems which thermalize, this is the microcanonical average. So E bar is the average energy between Em and En, and omega is the energy difference between Em and En. Okay? So unlike here, where there was absolutely no dependence of this quantity on the individual M's and N's, which is what I was saying. It didn't matter how far apart these were within the window. This actually puts that back in. So it says that that dependence is contained in this function, e to the power of minus s so s of E bar is the entropy at E bar, okay? And so this is the thing which is the equivalent of this exponential factor, e to the power of minus s of E bar is the equivalent of the d sitting here. And why is that? Because you know that for systems which thermalize, the entropy is going to be extensive in the number of degrees of freedom. It's an extensive quantity. So this is something which is exponentially small in the number of degrees of freedom, just like this object here, the Hilbert space dimension in random matrix theory. So this is the thing which ensures that your fluctuations are small and exponentially small in the number of degrees of freedom, okay? But the coefficient here is something which contains more structure, sorry, E bar here. It depends on the individual states, M and N. So again, as I said, there's no proof of this. This is a hypothesis. And as far as I know, it's also only been in any satisfactory sense been proven just for, the reason that it's very difficult to prove this is that this is what we are saying is going to happen for systems which thermalize, right? But systems which thermalize are systems which are not integrable. And so it's very difficult to do any exact calculations on it. The systems on which you have any hope of doing exact calculations are not these ones. So then, in order to prove something like this, you have to sort of relax the definition of what you mean by proof. So a strict mathematical proof of this for any system, as far as I know, has probably not been presented. But there's enough numerical evidence of this. In fact, the fact was that Deutsch and Srednitsky proposed this over 25 years ago. But this has sort of come back into focus only in the last decade because of the fact that extensive numerics have been done, and this has been verified for a large class of generic quantum systems which don't have any special symmetries and hence are not integrable, for generic operators, and found to be true. Okay, so that's what's really brought this back into focus. And now with, now that we have many body localized systems, which are a generic class of systems which don't thermalize, like a generic class of integrable systems in some sense, this has become an even more important thing. Okay. Oh, so the entropy here, so this is the entropy at this average energy, okay? So now for a system which thermalizes, you know that the entropy is an extensive quantity, right? Which means that the entropy is going to be proportional to the number of degrees of freedom. So here I'm thinking of a system which has a certain number of, it has some average energy, some number of degrees of freedom, n, and then I'm increasing the size of this while keeping intensive quantities the same, energy per degree of freedom, okay? And things like that. So then you know that the entropy is going to scale this way if I do that. So it's going to be extensive in the number of degrees of freedom. And here the entropy appears in this exponential up here, right? So it is, so these off-diagonal elements are going to be exponentially small in the number of degrees of freedom, just like you see there. Well, okay, so I mean, n to the power of d, well, I'd say it's n. No, okay, so exponential is e to the power of minus n, right? So s goes as this, so e to the power of minus s of e is is going to go as e to the power of minus n, whatever, some minus alpha n. So that's what I mean by exponential. Okay, so, right, yeah, it is log of t, the n, right, exactly. Okay, so now maybe let me show you some numerical data on random matrix theory really. So this is a confirmation of the original Wigner-Dyson idea. So what you have here along the x-axis is basically the energy level spacings of heavy nuclei normalized by the mean level spacing. So there was spectral data on, and I think this probably goes back to maybe the 50s or the 60s, I'm not sure when this data was obtained from various scattering experiments. And so the nuclear energy levels for heavy nuclei were reasonably well known. So one could get the energy level spacing data and then make this kind of plot. So here you have the energy level spacing divided by the mean level spacing. And this is the distribution of that from the data. And so the actual data are these steps, these discrete steps, because you don't really have a continuous distribution of these energy level spacings. You have some discrete energy level spacings which you get for some set of nuclei. And so that's one of the things which contributes to the steps. But you can see that the steps have this form. Now here is the Poisson form, just the exponential of minus s. And this is the Gaussian orthogonal ensemble form as predicted by Wigner and Dyson. And you can see that this fits the data very well. Okay? Actually, this is fairly remarkable because of the fact that in doing this, you are really not, in doing this calculation, you're not using anything from nuclear physics. Okay? You're not using any aspect, for instance, of the strong interaction between the neutron and the proton. I mean, much less any ideas of quantum chromodynamics that probably hadn't even been developed then. You're simply saying that the system is so complicated in terms of its Hamiltonian that it looks random. And the fact that it's random actually gives you the simplification in terms of calculating the energy levels spacing statistics, and you get this. So of course, there's no hope of calculating the energy level statistics, but the level spacing statistics become easy to calculate once the Hamiltonian is random, which is what this is. Okay, so that's for a real system. Now here's something where you can see the sort of level spacing statistics, the difference between this for an integrable system and a non-integrable system. So what we have here is we have a single particle in a two-dimensional box. Okay, so the particle in a two-dimensional box. On the left-hand side, we have the energy level spacing statistics for the box when it's a rectangular box. Okay, so when it's a rectangular box, you know that it's an integrable system because it separates nicely into, you only have the kinetic energy inside the box, and it separates nicely into a kinetic energy along the x-axis and a kinetic energy along the y-axis, okay? So those are the two conserved degrees of freedom, and it's a two-dimensional system, so it's integrable. So now you can look at the quantum mechanical problem of a particle in a two-dimensional box, rectangular box with sides A and B. So I don't know if you can read this. One of the things that's important here in order to make this thing look good is that A and B are incommensurate, meaning that A and B are not, A and B, the ratio is not a fraction, because if it's a fraction, then you end up having some degeneracies which can mess this up a little bit. So you want to avoid exact degeneracies. So you choose A and B such that the ratio is irrational and the product is also irrational. So that's pretty irrational. And so you find that when you look, so this is for 25,000 single particle energy level spacings. And when you look at the histogram and you make this plot, this fits very nicely to the Poisson distribution. Now here you have on this side, again, a particle in two dimensions, in a two-dimensional box, but a very odd-shaped box. Okay, it's a box which looks like this. So it's got these two straight sides, but then it has this curved side and this curved side. And for this, there are no conservation laws. So this is not an integrable system. So here, in fact, you can see that if you start the system out at some point, and okay, so what is this? So this is, you have a particle in this box. And classically, if you wanted to think of the motion of the particle, it's free inside the box, and every time it suffers a collision with the wall of the box, it's reflected specularly. So so the generic term for problems like this, at least classically, is that these are called billiard problems. Okay, so this is a particular kind of billiard problem in this kind of box. And so you can see that if you started so this is the classical trajectory, you started the particle out here, then it would, this is a fairly regular reflection, and then gets reflected here and here, and then if you allowed it to get reflected a few more times, then, and you looked at that trajectory, the trajectory would look really random. And in fact, here, if you started the particle out at some position which was quite close to this, and then let that trajectory evolve, you would see that after a sufficient amount of time, the position of the particle would be very different from what it would have been if it had started here. So you'd actually see chaos. Anyway, so it's this odd-shaped box, and this is not integrable. So you can again look at the quantum mechanical problem here, solve it numerically, obtain the energy eigenvalues, and what you see is something which is a nice GOE distribution. Okay? So in fact, it turns out that you don't even need something which looks so odd. You could take a rectangular box and take two of the sides, let's say these two sides of the rectangular box, and curve them in some way, something that's called I think the Bubinovich stadium, which is certainly a much less odd-looking box as compared to this, and even that would give you GOE statistics. Okay, so integrable, non-integrable system in a very simple case where the system just has 2 degrees of freedom, you can see the difference very clearly. Okay. So this is obtained for, you solve the particle in a box with the box looking like this, and then you obtain its energy spectrum numerically, and then you look at the distribution of these energy eigenstates and plot this. So what was your question about randomness here? See, the whole thing here is that there is nothing inherently random about this Hamiltonian, meaning that in some sense you're not putting in a term in the Hamiltonian when, let's say, you write it in a real space basis, which is some random variable. See, there are problems where you do that, right, which we'll talk about tomorrow, where, let's say, you write down a Hamiltonian. Okay, so what I'm saying is that it's simply this, that so this is the Hamiltonian inside the box, right? And it's 2-dimensional, so it's px squared plus py squared by 2m. And that's it. It's not like you're adding to this some potential or something with some random variable. That's not what you're doing here. The Hamiltonian inside the box looks simple. What makes it chaotic, what makes it look random, are the boundary conditions here, right? So you know that the wave function has to be 0 outside the box. So what is the shape that defines the boundary beyond which the wave function has to be 0? That is the thing which in some sense is, which is what is making this non-integrable, right? But that is not being incorporated by actually putting in any random elements into, into this Hamiltonian when you're expressing it in real space. It's really coming somehow from the boundary conditions. No, okay, so the thing is that here so what we are saying is the following. Okay, so let me just go back to what the statement of random matrix theory is. What is it that we've been doing all along? I give you one single Hamiltonian, okay, not an ensemble of Hamiltonians. Just one single Hamiltonian expressed in a certain basis, okay? So again, think of it in the way that I sort of was talking about it earlier, that you first define the Hilbert space on which this Hamiltonian is. In that Hilbert space, somehow close your eyes and pull out some basis, okay? So you've given me the basis. Now I give you my Hamiltonian in this basis. It's a matrix, okay? And that's it. There's no ensemble there. It's just one single matrix. And then you obtain its energy eigenvalues and eigenfunctions. You diagonalize it somehow. And you look at the level spacing distribution, okay? And the claim is that if the system is not integrable for that one single Hamiltonian, you will get an energy level spacing distribution which looks like this. Of course, for that you need to have a sufficiently large number of energy levels in the first place in order to even get a distribution from one single Hamiltonian as opposed to from an ensemble. And that is taken care of here by the fact that, the way you calculate this is, you essentially have in this problem an infinite number of energy levels. Like it's a particle in a box, right? So the Hilbert space of a particle in a box is infinite dimensional. So this is in principle an infinite dimensional problem, although when you're solving it numerically, you divide the box into cells, so you actually make it a finite dimensional problem with a large number of dimensions. And so you have a large number of energy levels that you get, and this is a level spacing distribution, okay? So here so this isn't an ensemble of Hamiltonians from which you've got this. You've got this for one single Hamiltonian, which is the Hamiltonian for this, with these boundary conditions. And the claim of random matrix theory is that the level spacing distribution that you will get for that one single Hamiltonian is what you would get had you plucked, the Hamiltonian out of an ensemble of Hamiltonians and done this kind of averaging. Okay, so let me just show you one last thing and then we'll stop. So this is something which I didn't really have the time to explain in detail. Okay, now maybe I'll leave this for tomorrow's lecture because I also need to then introduce the model with a slightly non-trivial. Okay, so I'll stop here. So tomorrow so one last bit of summary and then we'll end. So what we've done here is we've looked at random matrix theory. We've looked at mate from the point of view of random matrix theory. We've looked at a refinement of random matrix theory, which was the eigenstate thermalization hypothesis. I've stated it. So what I'll do tomorrow is I'll show you how mate emerges from the eigenstate thermalization hypothesis. But for us, thermalization is really might and not mate, as I told you right in the first lecture. So then after doing that, we look at how might comes about and how in some sense might doesn't even make a direct, might doesn't require this particular form of the eigenstate thermalization hypothesis. This is really the form for mate, where you're looking at the expectation values of typical macroscopic observables. That's the ansatz. So we look at what might means in the context of the eigenstate thermalization hypothesis and random matrices. And there we'll encounter something called canonical typicality, which is a very important concept, which is sort of in some sense the backbone of thermalization in quantum systems. And if time permits, which I suspect it won't, I'll tell you a little bit about what's called many-body localization, which is a generic quantum phenomenon of non-thermalization. The only generic family of systems we know, generic is important there, which seem to buck thermalization, which don't seem to thermalize. Okay? So that's what we'll do tomorrow. Yeah, it is GEO. Is there any way to know that it's GOE? Okay, right. So a priori, yes, there is a way to know that it's GOE because you know that the system has time reversal invariance, right? But let's say that I just gave you something like this, then if you want, if you want to know which ensemble it belongs to, just fit. I mean, if you have a good enough number of data points and a smooth enough curve, then you can actually distinguish between this and that.